Now let's go back to a related rates problem that is a word problem. It comes from a somewhat realistic situation. It's kind of a classic setup that makes puts all the elements of it together without being incredibly complicated. It's a conical tank. It's very similar to a problem you'd find in any book, especially Stewart. The overall height, so it's a conical tank with a vertical axis. And in fact, I'm going to go ahead and do the first step of the strategy, which is draw a diagram. Often this will be done for you, but in real life, nope. Doesn't happen. Okay, so it's a conical tank with a vertical axis, and the overall height is 60 centimeters. And the diameter of the top, note diameter, it's a common thing that can be confusing. Diameter versus radius, that's 30 centimeters. If we need the radius, we might as well figure that out right now. That's going to be 15 centimeters. Okay, that's the whole tank. Okay. Now water, there's a certain amount of water in there, and we're not quite sure right now how much water's in there, but we're told that it's leaving at a rate of 2 liters per minute. Uh-oh, we got to figure out liters in terms of centimeters. All right, we can do that. And then how fast is the water level changing when the depth is 20 centimeters? Oh, okay, so in fact, the depth, it's actually only like a third full in terms of height, and that's 20 centimeters, like that. Okay, but you know what? You want to be really careful about that, and this is a mistake that's pretty easy to make. I'd rather not put in that value, because, and notice that's the whole, how fast is it changing when the depth is 20 centimeters? They say that almost as an afterthought, and that is a hint that you don't want to put that as a constant in. Really, what's really important is that we're changing the water level, the height of the water. That's the variable that we're interested in, so that we're going to call h. And that's what we want to know. So this, what we really want to know is what is dH dt. Okay, so in fact, we're getting to the next steps of the process. Okay, so we've labeled the diagram, and this is the key thing. I want to label it with letters. And you can put numbers into it if you think it's constant. So this tank isn't actually changing shape, the metal or whatever it's made of. That's just 60, that's just 30, that's just 15. That's okay to put in as numbers. As fixed constant numbers. But this one really has to be a variable at this point. And only later will we come back and put in the 20. Okay, so what else is going on? Well, notice that we have the height of the tank and like the radius of the tank. We have the height of this conical bit of water here. If we're going to figure out the volume of that or relate it to the volume, we better understand the radius of that guy. And that's again going to be a variable. That's going to be r. So you don't want to put in a number for that either. Okay, so that's pretty good. And then, of course, we could also just put like, well, the volume of water, call that V maybe. The volume of water is going to be relevant. Okay, so we've got a pretty good diagram, by my standards anyway, my drawing standards. Okay, so express the given information and desired rate in terms of derivatives of the quantities you identified as step 2. Okay, so water leaving at rate of, okay, liters is a volume measurement. And leaving, that means that it's decreasing. So what we're given, really, is we're given that dV dt is minus, and we might as well watch out for units. Earlier the better. A liter is 1,000 cubic centimeters. And so we're just going to convert that. I'm going to just make the units consistent. So liters is going away because everything else is centimeters. 2,000 cubic centimeters per minute. So that is a rate that's given. Okay, and we've watched out carefully for signs because it's the water's leaving the tank. The volume of this conical bit of water is decreasing. Okay, and we want to know dH dt equals what? Okay, so as far as we know, V and H are the relevant things, but I've already given you a hint that R is going to be real crucial as well. Okay, so let's write down a master equation. Oh, went too far. Okay, so master equation is going to be the volume of a cone, and that is something, it'd be great if you memorized it. Often we rederive it in calculus, but usually later than this. That's 1/3 pi, but it's often given in like tests and things like that. 1/3 pi r squared h. And that's why the r is crucial, is that if you've got a cone, usually the way you get the volume of that cone is you know the height and the radius, the base radius, so it's kind of a base on the top of the thing here. And so R is going to have to come into this. So, and this is where if there are more than two variables, there's two possibilities. It's like, hey, nobody ordered R here. They're giving me dvdt and we want dHdt. Uh-oh, we're going to have to figure out R somehow. Okay. So if all but one rate of change is given explicitly, that's like in the previous problem, then you go to step 5. That doesn't happen here because dRdt was not given. And it's important we'll realize why, because we can actually figure out how R comes into it without being given a separate piece of data for dRdt. Okay, so usually what happens here is, say there's 3 variables like here, only one rate is given, you need to find an auxiliary equation. Okay, something that's always true and relates to the variables, just isn't quite as astoundingly important, front and center, let's say, as the master equation. And indeed, and I give you a big hint here, similar triangles comes in a lot with these things, and this is exactly what I was thinking. This is probably the example I was thinking of when I wrote that. We've got, if I just look at the cross section, so let's erase some stuff. Okay, I think I do need to leave that 20 centimeters because I don't want to forget that. Okay, but just look at the cross section of, let's say, half the tank. This is a very common thing. You've probably seen this before. When you have a 3-dimensional problem, a lot of the time, the heart of it is really just 2-dimensional. This is all symmetrical around this axis. What really matters is just a cross-section, in fact, even a half a cross-section. So the whole tank, it's 15 radius when it gets up to 60 height, or 60 depth, let's say. And we know we are at some h here, and we want to know r here. And so similar triangles just tells me that r over h is 15 over 60, is 1/4. And so r is just h over 4. That's a fact. It's also always true. This is always true about a cone. This is always true in this particular case about r and h when that cone is a part of this bigger cone. And so this triangle cross-section is similar to the big one. So watch out for those things. And often people miss that. Okay, so there's a couple strategies from there, but the most straightforward one usually, and the one I usually recommend, is solve the auxiliary equation for the unwanted variable. We really don't care about r here, so we actually solve for it, so that means we can then substitute in and get it out of the master equation. Okay, so we've already done that, r equals h over 4, and then we substitute into the master equation. Okay, so we're going to get what I would call the new master equation. V is 1/3 pi. R squared is the quantity h over 4 squared times h. And so we get, let's see, pi over, looks like 48 h cubed. Let me just put the v equals. Okay, that's our new master equation. Okay, so there's other ways you can deal with that you might see in some other presentations, and they totally are valid, but usually this is a nice way to deal with that. So r, the variable we don't care about, has gone away. Okay, so now we're good. Now we can differentiate the master equation. It happens to be the new one. Let's see. I really don't want to erase too much. Sorry, it's going to get a little cramped for a minute here. Okay, let's just differentiate it here. dv dt. Okay, the derivative of h cubed is 3h squared, but times dh dt, and then times the constant. Get a little bit of a cancellation, and you get pi over 16 h squared dh dt. Okay. Now, and so the chain rule, again, absolutely crucial. Derivative of h cubed is not just 3h squared, it's 3h squared dh dt, because we're differentiating with respect to a different quantity, different variable. Okay, so now I say look careful at the units, and again, really the earlier the better, and we have rationalized things that dv dt we're about to plug in terms of cubic centimeters per minute. dh dt, h is in centimeters. Aha, that's where we're going to plug this in finally. And so we're going to get something where dh dt is going to come out in centimeters per minute. That seems fine. Okay, there's no issues about radians or degrees or anything like that either. Okay, but there's a lot of angle problems where you'd have to do that. Okay, so now we're going to plug in the values. So let's see, finally we can use that. So minus 2,000, oh actually, let's just do it right here. Okay, so minus 2,000 cubic centimeters per minute is pi over 16. Now we plug in the fact that, okay, it happens to be that at the instant we care about it, we know the depth is 20 centimeters, so that's finally where we can plug that in. So 20 squared is 400 times dH dt. Okay, so this equals this. Okay, we can do some cancellations there. Ooh, a 400 actually nicely cancels that down to just a measly 5. Okay, and I know it's getting a little scattered. Oh, well, but finally I can erase that. Okay, so fresh. Okay, and so we get minus 5. Let me just rewrite it. Getting close. Don't worry. It's not going to be too long. Is pi over 16 times our quantity that we want to solve for. Multiplied by 16 divided by pi, and you get minus 80 over pi. Ooh, and this was a square centimeter. Sorry. Ooh, see, I'm not being careful with units. That wasn't a good idea. This is really 400 square centimeters. That cancels this down to just centimeters per minute. But notice what I did. What happened is I thought, wait, this is supposed to be a length or a height or depth or whatever. With differentiating with respect to time, that should just be centimeters per minute. Why is it still cubed? It's because I forgot to put units into a quantity there. Okay, and we're done. Equals dH dt. Notice you want to check, is it coming out to be the sign you think it should be? It's going down. If the water's leaving the tank, then H is decreasing. The height or depth or whatever you want to call it of the water level is decreasing. Okay, so we plugged in, we solved, we were careful with units. Oops, yeah, that's step 8 right there. Okay, no radians, degrees, or anything. And that's, let's see, minus 80 over pi, that's roughly like minus 25 centimeters per minute, something like that. And then maybe do a reality check. If it's like 25 million, I don't think so. If it's minus 0.000025, I don't think so. But it seems fairly reasonable that water's leaving this tank at a pretty decent rate, and it's going to take, looks like it's going to take less than a minute to empty this thing out. Okay.